Hello everyone, my name is Humaira Banu. I'm currently in my second year of studying computer science and engineering at Srinivasa Ramanujan Institute of Technology, Anantapur. Today I'll be discussing how finding the coefficient of generating functions. So this is the topic of mine today in discrete mathematics and graph theory. So let us see what is the outline of my topic. Recurrence relation, recursive functions, a sequence of generating functions, one example problem and the solution of that problem, and finally conclusion. Right, starting from recurrence. So first of all, see what is a recurrence relation. Sometimes it is very difficult to define an object. However, it may be very easy to define these object of itself. So this process is known as recursion. We can see recursion to define sequence functions and sets. And the second one is recursive functions. We can use two steps to define a function without the set of non-negative integers as its domains. So basic step, first one is basic step, that is specify the value of the function at 0. And the recursive step, give a rule for finding a value from its previous values. So these are the recursive functions. So let us see what are generating functions of a sequence. Consider a sequence of real numbers, that is a0, a1 and so on up to an, and there exists a function f of x whose expansion in a series of powers of x is equals to f of x is equals to a0 plus a1x plus a2x square plus so on up to an x power n and up to infinity. So in summation form, this sequence can be written as summation of or equals to 0 to infinity a or x power or. This is the summation form and which is a short to represent the above given sequence. And then f of x is called generating functions for the sequence a0, a1 up to so on an and up to infinity. We can also define the generating function in a mathematical way to write the sequence of numbers as a mathematical power series expansion. So here I have mentioned some examples with the formulas. So the first one is 1 by 1 minus x. See, the denominator can be written in numerator by giving this inverse whole power minus 1, and this expansion is 1 plus x square plus x cube and so on up to infinity. And in summation form it is summation of or equals to 0 to infinity x power or. It's a simple one. And similarly, when it is 1 plus x whole power minus 1, we'll add the alternate minus, like here in summation form we have to mention minus 1 whole power or to get this alternate minus symbols. The next one is 1 by 1 plus ax. Similarly, to get this into numerator form, we'll giving the inverse in power, that is minus 1, and the which is equals to 1 minus ax plus a square x square minus a cube x cube plus and so on up to infinity. And in summation form, it can be written as summation of or equals to 0 to infinity, as to get the alternate negatives on the 1 by 1 terms, we have to mention this minus 1 whole power or a power or x power or. And for 1 minus ax whole power minus 1, no need of mentioning this minus 1 whole power or, as all the terms are having the what we say that addition operation. And similarly, we are having these two examples and the summations of those examples. So example problem, like find the coefficient of x power 18 in x plus x square plus x cube plus x power 4 plus x power 5 into x plus x square plus x cube plus x power 4 plus and so on infinity whole power 5. The solution of the given problem is like, first of all I have written the given that all the sequence. Okay, so for this we are not having any direct formula to get the solution. So for that reason I have taken this x common in the first function, and in the second one I have taken x square as common, x power whole power, as the power 5 belongs to the whole term. I have taken the x power 5 as also as common term. After that, adding these two, adding this x and x power 10, will be getting x power 11 sequence. on the sequence. 1 plus x square plus x cube plus x power 4, and after taking x square whole power 5 as common, the remaining terms. After that, this sequence can be written as 1 minus x whole power minus 5, and this as it is. After using this all these formulas, we'll be getting the summation, like summation or equals to 0 to infinity c of 5 plus or minus 1 comma or power sorry x power or. So here the n value is 5, and after solving this we'll be getting 4 plus or comma or. And to get the value of or here, we'll be equating the powers. Like for suppose we want the coefficient of x power 18, right? So for that we'll be equating this x power 18 with x power 11 plus r, what we have got here. So by equating both this, we'll be getting or value as or equals to 7. So substitute this or equals to 7 in wherever or values are present. So here C or equals to 7 we have substituted. We'll be getting C of 11 comma 7, and the whole remaining sequence. 11C 7 value as well as these sequence value. When we multiply this with all each and every term, we'll be getting 10C6 and 9C6, 9C5, 8C4 and 7C3. After doing all these after doing all these values, after simplifying, we'll be getting the final value or final value as 1. This is the coefficient of x power 18 in the given sequence. So finally, moving to conclusion. In summary, finding coefficients of generating functions is a powerful tool for solving combinatorial problems. It allows us to represent sequences algebraically as well as efficiently extract specific terms. By using methods like power series expansion and recurrence relations, we can solve complex counting problems and gain insights into sequence structures. This technique is essential in fields like combinatorics, number theory, and also in algorithm design. So thank you for your attention.